So,
yes,
welcome to the conference, and please you can start giving the talk, and I suggest that the discussion happens as in the previous case at the end.
Okay, yes, thank you. Okay, so today I will discuss the theory prediction for the muon G-2, and more precisely I will focus on the hadronic contribution to this observable. So most of these slides are based on this review that was published earlier this year. Okay, so I will start with very basic stuff. So as you all know, so the muon in the standard model is an elementary particles, which is very similar to the electron, but about 200 times heavier. And like the electron, it is a spin 1/2 particle. So it means that it has a magnetic moment, which is proportional to its spin, with here G, this proportionality factors. And then the anomaly is simply defined by the deviation of this G from 2 divided by 2. So then the first question is, why is it interesting? So there are mainly three reasons. So first, this observable can be measured very precisely by experiments. And at the same time, it can be predicted very precisely in the standard model of particle physics. And finally, this is also an observable which is quite sensitive to new physics. Okay, so in a more formal way, so if we use the symmetries of the theories, then in this case, we are interested in this QED vertex function, and we can show that it can be written in terms of two form factors. So the Dirac F1 and the Pauli F2 form factors. Then F1 is the normalization of F1 is just 1 due to charge conservation. And then at the origin, F2 is given by what we want, so by this anomaly. So it is 0 at the classical level, and this is a purely quantum effect. So yeah, just as I said, so yeah, at the classical level, so from the Dirac equation, G is exactly equal to 2, and so mu equals 0. But then in the quantum field theory, it will of course be different from 0. And the first correction was completed by Schwinger more than 70 years ago. And this is the famous first order correction, which does not depend on the mass, which is the same for the electron, the muon, but also for the tau. Okay, so of course, since we are interested in this QED vertex function, the dominant contribution is from QED corrections. And they indeed account for more than 99.99% of the final result. And in this case, they can be computed very precisely using a perturbative expansion in alpha. And so now the 5-loop contribution is also known. So here I show the diagrams for at the order alpha 4, alpha 6. So, and you can see that the number of diagrams increase rapidly with alpha. And for the order 8 and 10, of course, people need to use numerical methods to generate and compute all the diagrams. Now, the good thing about this perturbative expansion is that it converges very fast. And in this table, you can see the contribution of each order in alpha. And now we know this 5th order contribution. You can see that this 5 here is already small, I mean, much smaller than the uncertainty that we currently have. So which means that these QED corrections they are now well under control. And in that sense, it is also a very strong test of QED itself. Then beyond QED, we also have electroweak corrections. So in this case, they are expected to be a bit smaller because of the relatively heavy mass of the gauge and Higgs bosons. And in this case, they are known up to 2-loop contribution. So here I showed some example for the 1-loop contributions. And so including the 2-loop contribution, we end up with this value here. So with the precision better than 1%. And again, to give you an idea, so this value here is about 4 times the experimental error. So it is not negligible, but knowing that we have a precision better than 1%, it also means that this contribution is completely under control. And then what is left are QCD corrections. So of course, quark and gluons, they do not couple directly to the muon, but then they QCD will appear via loop diagrams. And so the two main contributions that we will discuss today are this what is called hadronic vacuum polarization, which enters at the order alpha squared. And here on the right, this hadronic light-by-light scattering, which enters at the order alpha cube, where this red blobs contains all the non-perturbative information. And then, of course, in principle, there can be contribution from unknown particles or interactions. And usually they will scale like the mass of the lepton, so in this case, the mass of the muon squared, divided by some typical scale from this new physics. This is m lepton squared, which makes this muon much more sensitive to new physics compared to the electron. So in principle, there are also other QCD corrections. So here I show more exhaustive list. You have also so this what is called NLO and NLO HGP contribution. But so in practice, they can be obtained. So they are similar to these first diagrams, except that there are more either more photons line or 2 times these red blobs, and they can be computed in a similar way as the leading order HGP, just a different QD kernel function, but they're also much smaller, and so they are now well under control. So really the two important diagrams are this leading order HGP and this hadronic light-by-light scattering. Okay, and so this is the theory status as published so in June of last year by the muon G-2 theory initiative. And here I list again all the contributions. So with these big QD contributions, these relatively small electronic contributions, and then those hadronic contributions. And so from the error, again, you can see that the final theory error is completely dominated by the HGP and the hadronic light-by-light contributions. But all the other contributions are perfectly under control. Now, here it is the experimental status after the first run of this Fermilab experiment. So the results were published a few months ago. So here in blue, you can see the previous measurement at Brookhaven in 2004. And here in red, this is this new measurement. So okay, first we can see that it is in very good agreement with Brookhaven, which means that we can also take the average of these two measurements, and then we end up with this purple band. And here in green, this is the theory prediction that was discussed in this slide. So we can observe, and so if we take these two estimates, then we observe like discrepancy of about a bit more than 4 sigmas. Now, again, this discrepancy is quite large because it is, in terms of magnitude, it is about 2 times the full electronic contribution. And then second, this error is mostly due to hadronic contribution. And since this value here is just the result of the first run, which is, and after all the runs, we expect to have something like 20 times more statistics, then this error would be significantly reduced in the next few years, which means that at the same time, we would like to also reduce the error on the theory estimate. Now, what is important to know is that in this standard model estimate, lattice QCD results were not really included, at least not the most recent one, which means that for the hadronic, so since the publication of this value, there is a new complete calculation by the Mainz group of the hadronic light-by-light contribution, and also there is the first sub-percent calculation of the hadronic vacuum polarization by the BMW collaboration, which, as we'll see later, tends to reduce this tension. Okay, so here I show again these two hadronic contributions. So for the hadronic vacuum polarization, in this case, what we want is a precision of a few per mil, so basically 0.2, 0.3%. So this is what makes this calculation very challenging. And for the hadronic light-by-light, in this case, it is a much more difficult calculation because in this case, we have to consider the full hadronic light-by-light tensor, which means that, okay, first we have more Lorentz indices, but we also have more momenta, which means that, for example, it is more difficult to disentangle what is low and high momenta contributions. But at the end, it is also a smaller contribution because it is a alpha cube. And so in this case, just 10% will already be enough for to reach the same precision on the experiment. So these two calculations are difficult, but I would say not for the same reason. In the first, for the HGP, it's really because we want to do precision physics. In the second case, it's more because what we have to consider is a very complicated four-point correlation function. So I will discuss these two contributions in this talk. And so to compute this contribution, we have mostly two first principle approaches. So the first one is the dispersive framework, which is based on analyticity, unitarity, and all these properties of the theory, but it also relies on experimental data, which means that first we need experimental data, and then we have to be careful with the propagation of the errors to the final result. So it has been used very successfully for the HGP and more recently also for the light-by-light, even if in this case we will see that it is a bit more complicated. And then you can also do full lattice QCD calculations. And in this case, the challenge is really to control of the different sources of systematic errors, which is quite challenging at this level of precision, especially for the hadronic vacuum polarization, where we want to reach the pyramid level. But fortunately, we also have many groups working on this, and which means that there are a lot of cross-checks that are possible between different collaborations. So at the end, the idea is that we should have two independent estimates, and if they agree together, then it makes us confident that we can compute this contribution in a safe way. Okay, so I will start with the hadronic vacuum polarization. And so here I start with a summary of the result. So in the bottom, you can see result from the error ratio. So this is this data-driven approach. And on the top, you can see lattice result. So you can see that most lattice results, they tend to lie a bit above the dispersive result, but with relatively large error bar. So there is no, I mean, independently, there is no big discrepancy between any lattice result and the error ratio data, except now for the BMW collaboration that published recently this first sub-percent calculation. Okay, so yeah, so I will explain how it is computed using the error ratio, and then I will come to the lattice. So in the dispersive framework, so basically the idea is to use again this analyticity and optical theorem to relate mu to this error ratio. And then basically what we have to do is just a convolution between this error ratio and some QED kernel, which is known analytically from threshold to infinity. So here I show some experimental value for this error ratio. In practice, what is done is that at low energy, so between 2 GV, we can use the data, and then above some threshold, from 2 to 3 GV, we can use perturbative QCD. And then we just have to include some resonances above 3 GV. But so here, basically, the main challenge is just to combine all those experimental data sets from many different experiments. So and here I show some results from two publications here, and here in green, this is the result published in the white paper from the muon D-2 theory initiative. So you can reach a precision of about 0.5%, depending on the estimates. And you can also see that there is a relatively good agreement between all the estimates. And more importantly, you can also see that, for example, if you look at the white paper estimates, the main source of errors are the statistical one, but also what is called here this Chloe-Baba error that we will discuss in the next slide. So yeah, apparently there is a good agreement between this different estimate, but now when we look at the details, it is a bit less nice. And in particular, if we look at the 2 pion contribution. So of course, the main drawback of this data-driven approach is that it depends on experimental data. And unfortunately, for the 2 pion channel, which is the dominant one, because it contributes to about 70% of the full signal, we have a local discrepancy between different experimental data set, and in particular between the 2 most precise ones, so the Chloe data and the Babar data are shown here, which are in tension. And so here I show the cross-section between 0.6 and about 1 GeV. And in this energy range, I mean, the difference between Babar and Chloe is of about 10 in this unit of 10 to the minus 10, which is not small compared to the difference between the theory and the experimental value for G minus 2. So it's really 1/3. So it is, I mean, this discrepancy is too small to fully explain the discrepancy, but at the same time, it is absolutely not negligible. It needs to be understood. So, I mean, recently, SND has published a new more precise data set, which is not yet included in this estimate. And so the second possibility is to use lattice QCD. And so in this case, what we have to compute on the lattice is basically this 2-point function here of a vector forms. So we want to compute this vacuum polarization tensor, which can be expressed in terms of a single scalar function. And this single scalar function can be then computed on the lattice from this vector 2-point function projected on a given momentum Q. And then we just have to integrate this subtracted vacuum polarization function times this F, which is again a QED kernel that is known analytically. Now, it's not on the lattice, it's not very convenient to use Q as a variable because we work in a finite volume, and so the value of Q that we can reach are discrete. But then it was shown by in this paper that we can also compute mu as in position space, which is much more easier on the lattice. So as an integral over this Euclidean time times a new QED kernel times again the vector 2-point function, but this time projected at 0 momentum. So in principle, it is a really easy calculation because we just need to compute a 2-point function, which is one of the simplest quantities that we can compute on the lattice. So again, the difficulty will come from the fact that we want to reach the per-mil precision. So if we consider for now only isosymmetric QCD, it means that we have two contributions that we want to compute. So this one, which is called the connected contribution, and this one, which is called the disconnected contribution, where, of course, I mean, in lattice QCD, we always have to remember that the gluons are summed to all orders non-perturbatively. So these two loops, they are always linked by gluons. Okay, so as you probably know, so any lattice QCD calculation, I mean, suffer from statistical errors because we use a Monte Carlo algorithm to estimate the path integral. And here it is quite bad because this noise over signal increase exponentially with the Euclidean time. So at large time here, it means that this function here will be very noisy. And then, of course, we have to deal with different systematic errors. The first one is the continuum extrapolation. So, of course, any lattice calculation is done at a finite value of the lattice spacing. And at the end, we need to use several lattice spacing to extrapolate to the continuum. We also need to take the infinite volume limit. And for this, we can use some theoretical tools. In some cases, we also need to do an extrapolation to the physical pion mass, but now this is less and less a problem because most collaborations are using physical pion masses, or at least one ensemble with a physical pion mass. And then to reach this sub-percent precision, we also need to include QED and strong isospin breaking correction. These are the main systematics that we need to include in our calculation. Now, the good thing is that, as I said before, there are many collaborations working on this, and most of them use different lattice actions, which means that even if they are all equivalent in the continuum limit, they all have different features at finite lattice spacing, and so different kind of systematics. And so at the end, if all collaborations agree with each other, it is a very strong cross-check. Okay, so on this plot here, what I show is the integrand. So if you remember, we have to integrate the kernel times the two-point function as a function of the Euclidean time. And here I show the integrand for the light quark contribution in black, the strange quark contribution in blue, and for the charm in green. And for the charm and the strange, so the signal has been multiplied by a factor of 6. So they are much smaller than the light quark contribution. So here you can see that indeed for the light at long distances, the signal start to be a bit noisy. This would be one of the main difficulty. And also the light quark contribution is much long range compared to the charm or the strange contribution, which on the lattice means that we expect relatively large finite size effects. And indeed, for typical lattice simulations, at the physical pion mass, we have finite size effect of the order of 3%, which again is not negligible since we want to reach a few per mil precision. And you can see that the light contribution contributes to almost 90% of the total contribution. And isospin breaking correction, so QED and strong isospin breaking correction, it's about 1%. So again, it is small, but not negligible at this level of precision. So okay, now I will discuss these 4 different systematic errors. So I will start with a signal over noise problem. So in this case, there is a very elegant way to deal with it. So on the lattice, if you look at the vector-vector correction function, you can simply insert here a sum over all intermediate states. And this sum is a discrete sum of the lattice because of the finite volume. And so the idea is that if using a different lattice QCD simulation, you can compute these energies and this overlap very precisely, then you can reconstruct this two-point function by inserting more and more states in this spectral decomposition. So this is what is shown in these 2 plots by the MINDS collaboration and here by the RBC UKPC collaborations. So in black, you can see the raw lattice data, which start to be noisy at long time. And then the different colors correspond to including more and more states to saturate this sum. And so at long distances, so let's say after 1.5 or after 2 Fermi, only very few states need to be included to saturate this sum. And here, by doing this trick, the signal, the noise of our signal increases only linearly with time instead of exponentially. So it is a way to solve this statistical noise that we have in our simulation. Another trick that are used by other collaboration is also, there are also algorithmic trick, like what is called this low mode averaging, which in practice means that we can compute this exact all-to-all propagator instead of the point-to-all propagator, and which means that we can really average over the whole lattice and then again reduce the statistical error. Then the second difficulty is the finite size correction. So in this case, again, since these finite value effects are mostly due to the pions, we can use KIPT to estimate them. So it is now well known that NLO KIPT is not enough, but now the NN LO correction have been computed. The corrections are quite large. Yeah, but a second method is also based on what is called the time-lag pion form factor. So here the idea is that in infinite volume, we can write the spectral decomposition of the isovector contribution, which is given here in terms of the pion form factors that can be measured experimentally. And now in finite volume, you can use a similar formula. So again, we can write the spectral decomposition, but in this case, because we work in a finite volume, this spectral decomposition is again a finite sum. And then you can estimate the finite volume effect by taking the difference between the infinite volume and the finite volume. Knowing that these overlap factors here are also directly related to the form factors that can be obtained from experiments. Even if in practice, at this level of precision, we can use also a simpler model for FPI, like Gunnar-Sakurai parametrization or something like this. And then so by using this, so the typical lattice, we indeed obtain something like of the order of 30 in this unit of 10 to minus 10, which is about 3% of the total contribution. So here is a result obtained from the Mainz group, but similar results have been obtained by different collaborations. And then more recently, so in their publication, this BMW collaboration, what they did is that they were able to do a direct lattice calculation in a very large volume. So with an 11 Fermi box, where usually people concentrate in use more like 6 Fermi boxes. So in these 11 Fermi boxes, we can consider finite volume effect to be extremely small. And then by comparing with the 6 Fermi box, they observe the correction of about 18 in this unit of 10 to minus 10, which is not very far from this estimate here. So I will say that now this finite size correction is quite well understood, at least at the percent level precision. Now, if we really want to reach the per mil precision, probably we need to reduce this error even more. And then finally, as I said, so most lattice QCD calculations are done with QCD only, and also usually with the assumption that the mass of the U and D quark are equal, which is not exactly true in nature. And so we have to correct for QED and strong isospin weighting effects. So in principle, they are both of the order of a few percent, and they're also quite challenging to compute. But it's also important to explain that in principle, only the full QCD result with QED and some isospin weighting correction can be compared with experiments. And if we don't include QED and isospin weighting correction, then we are left with the isosymmetric QCD theory, which is not uniquely defined, and so there is some scheme dependence in its definition. So at the end, it's important that collaborations agree on what is called isosymmetric QCD and how to include the consistent way QED correction and isospin weighting effect. And for that, there are mostly two strategies. The first one is to expand the path integral in terms of alpha and the small mass difference. It's just a perturbative expansion. This is quite nice because it means that we can reuse all this isosymmetric QCD simulation that we did in the past. Now the problem here is that we have to put QED in a finite volume, which means that we expect to have a relatively large finite size effect, even if it has been shown that there is no, the first contribution in 1 over L squared is not there. So the first contribution scale as 1 over L cube, and so they might be relatively small, maybe negligible at a level of precision. And then the second strategy is to generate completely new gauge field configuration using using QED plus QCD in the path integral and so in the Monte Carlo algorithm. So in this case, the main difficulty is that we have many more diagrams to compute. So here, so if you remember, in the isosymmetric limit, we had only these diagrams without the additional photon. Now we have here 3 additional diagrams for the connected part. We have also 3 additional diagrams for the disconnected part. And if we also consider QED for the C quark and C gluons, then we also have these 4 additional diagrams. So in the electroquench, for these first 2, for the top diagrams, we have a result for now 3 collaborations, but always only for a subset of the diagrams, which are expected to be dominant. And those ones were unknown until recently, but in their publication, BMW, they were able to compute for the first time all of the diagrams. And at the end, they were able to conclude that they contribute to about 1% of the full contribution. So again, since we want a few per mil level, it means that we need also to know this contribution with a question better than 10%. And finally, the last difficulty is to do the lattice spacing and to perform the continuum extrapolation. So, of course, any lattice simulation provides a result in what we call lattice units. So it means that we don't have for example, m pi or the point decay constant, but what we have is m pi in unit of the lattice spacing. So at the end, if we want to know m pi or f pi in physical units, we need to know the lattice spacing also in physical units. And this is what is called the scale setting. Now, in principle, it looks like it is not a problem for mu because it is a dimensionless quantity. The question is why it matters. And the main reason is because in our simulation, the muon mass is an external scale. And so at the end, it means that we need to know the muon mass in lattice units. So we need to know lattice spacing very precisely. Actually, it has been shown a few years ago that so if we know the lattice spacing with relative precision given by delta alpha to alpha, then the relative precision on mu will be 2 times this. It means that if you know the lattice spacing with a precision of 1%, then you have automatically 2% precision on mu. And so if we want to reach the per mil level precision of mu, we need to know the scale setting at the level of 1 per mil, which is probably one of the biggest challenges for lattice calculations. Okay, but in the calculation, BMW, they use what is called they use the omega baryon mass to set the scale. The main reason is because in this case, it is based on a 2-point function. It can be measured relatively precisely on the lattice, and also it is not too difficult to include QED corrections. Some collaboration also use the pion decay constant to set the scale. In this case, the difficulty is to include QED corrections. And finally, even when we know the scale, again, we have to perform this continuum extrapolation, which can be quite difficult in the lattice. So again, here is this summary plot. This purple band are so the precision of this purple band corresponds to 0.5% more or less, and the final goal is to reach 2 or 3 per mil precision. So in the recent year, we have seen a lot of progress from lattice QED calculation, especially since this new BMW collaboration publication. And the hope is that at some point we will be able to average over dispersive and lattice data. But of course, before doing that, we need an agreement between these 2 values. And so it is very important to understand why this BMW data is a few sigma above the error ratio estimate. And so for this, what we would like to do is to build a new observable that could probe this tension. So now we have in the 2 incompatible determination. And so if you want to conclude or not on the presence of new physics, we need to understand this the agreement between these 2 values. So the idea is to build will be to use a different observable, but which is based on the same input. So on the lattice, it means the same vector correlator. And this observable should also, of course, be easy to compute and less affected by systematic errors, and ideally also statistical errors to make it cheap to compute. And this observable is what we call this window quantity, so which is defined here. So if you set W equal to 1, you just end up with the previous formula, which is just the full HGB contribution to mu. So now we will just multiply this integrand. So this G is a two-point function, K is this QD kernel times a window quantity. And so here I show in red, black, and blue 3 different windows, which are called the short distance, intermediate distance, and long distance windows. And here in gray, you see what I have shown before, so the integrand for typical lattice data. So this is G times K. And these 3 windows are built in such a way that if we sum over the 3 windows, then we end up with a full contribution. Now, the idea behind this is that if you look at so in the short distance window, basically it will be statistically very precise because the data here are very precise, but it will be affected by relatively large discretion effect. Now, at long distances, you are affected by this noise problem at large time, and also by large finite volume correction, and for staggered quark, also by what is called taste booking effect. But now, if you look at the intermediate distance window, we have a very good statistical precision and also small statistical effect. So finite volume are relatively small. Discretion effect will be also a bit smaller because we exclude the very short distance contribution. And so in principle, this intermediate window is much easier to compute on the lattice. So we can use this as a cross-check between, for example, different lattice collaborations. In addition, here on the lattice, it is also possible to do a flavor decomposition. And so in the next, I will focus on the light quark contribution. And so here, as a result, for this light quark contribution for this intermediate window, in blue, you can see the published lattice result. In blue, the preliminary lattice result.